The molecule shown here is the alcohol that is present in alcoholic beverages. Because this molecule has been known for a very long time, after all, this was Christ's first synthesis, this molecule has many names. However, if we had these many names to deal with for every molecule, we'd very quickly run into problems. There are more than 141 million small molecules and 67 million more DNA and protein sequences. We need to have a systematic way to name molecules so that every name leads us directly to the structure of a molecule. We build up these names just like we build up our own descriptions of anything in English. We have a noun, and if that noun doesn't sufficiently describe the thing, we add an adjective. If the adjective doesn't sufficiently describe the thing, we can add more or add an adverb to modify the adjective, and so on. Take this picture, for example. You might choose to describe this picture with the word dog. I know it's Clifford, but just bear with me. I could show you a picture in more detail, and you might now describe it as a red dog. But if the red really isn't a true red, maybe you need an adverb to describe the red. Maybe now it is a ghostly red dog. Molecule names are built up in the same way. Simple molecules can be named with the simple noun versions of the name, so to speak. If a molecule is more complicated, we modify the name just like we would do to describe something in English. And if the adjective part is incomplete, we can add modifiers like adverbs for that too. So notice the same thing is true for the heptane. If we've got just a simple molecule, we can name it with just one part of the word. But if we have something coming off of that chain of carbons, we now have to modify it. And if we have something coming off of that chain, now we have to modify the name for that chain. So a heptane becomes a 4-ethyl heptane, which then becomes a 4,1-chloroethyl heptane. The system that we use to assign names to molecules is called IUPAC nomenclature, IUPAC, where IUPAC stands for the International Union of Pure and Applied Chemistry. IUPAC nomenclature rules actually come in volumes, tomes if you will. A tome, the blue one, deals specifically with organic nomenclature. That being said, most simple molecules follow simple patterns when they are named. We figure out which functional group on the molecule is most important, and figure out how many carbons can be continuously connected and include that functional group. That's steps 1 through 3 as listed. Then we number the molecule and add the adjectives, which include numbers, alphabetically. Every once in a while we might need a prefix to indicate something special about the molecule. That's steps 4 through 7. We'll go over each of these parts in more detail. The first thing we always need to name a molecule is to figure out what the noun part of the molecule will be. We call this the main chain. The main chain will always contain the highest priority functional group, and the suffix for the main chain will reflect that. We'll start out with the simplest molecules, which are alkanes. Alkanes are always named with the suffix ane, A-N-E. Notice this matches the end of the word alkane. The other part of the molecule will indicate the length of the longest chain of carbons that contains the functional group by way of a prefix. The table shown shows the names of alkanes with lengths from 1 to 10. The first part is the prefix for length. The second is the ane to indicate that they're all alkanes. These prefixes come up really frequently, so you need to memorize these prefixes. You absolutely need to memorize the prefixes from 1 to 10 that indicate length of a chain. Molecules don't need to be in straight lines. They may include rings. The only difference in the names of cycloalkanes, the ones that are in rings, is that they will be preceded by the name cyclo. So if we look at propane, a 3-membered ring would become cyclopropane, or a 4-membered ring becomes cyclobutane. Now let's talk adjectives. Because we can't count on every molecule to be straight, we need to be able to label groups of carbons that come off the side chains, or substituents we call them. There is no need to reinvent the wheel for naming. We're going to use the exact same length prefixes that we use for main chains. But we don't want them to look like main chains, so we'll change the suffix from ane to il, Y-L. Side chains will always end in Y-L. Notice that the substituents, another name for a side chain, can be rings or straight chains. So we can have both rings that are side chains or straight chains. Also notice that there are shorthands for methyl, ethyl, propyl, and butyl. So the methyl shorthand is just Me, ethyl is Et, propyl is Pr, and butyl is Bu. The other thing that we need for most side chains is a locator, which is just the number of the carbon along the main chain where the substituent is connected. So if we have something connected on the second position, we just put a 2 in front of it. Let's work through an example. We are always going to name these molecules like an English phrase. The thing itself, the main chain, is placed after its descriptor, in this case, the side chain. The longest chain of carbons we can get on this molecule is 4 carbons long, which should correspond with a butane. We also need an adjective for that branch. The branch is 1 carbon long, meth, and a side chain, so methyl, methyl, as opposed to methane. Putting it together, and it is a methyl butane. The methyl is coming off of a particular position, so we need to give that a number. If we number the main chain from left to right, the methyl is on the 2 position, so 2-methyl butane. We don't always number left to right, but we do number so that the most important, or the highest priority, side chains have the lowest number. So we could have numbered from right to left, but we would have ended up with a 3 instead of a 2 for the number on that methyl, and we chose the lower numbered version. Not everything can be in the main chain. The rule is that the longest continuous chain of carbons is the main chain. But these rules are really guidelines. IUPAC allows for alternate naming when molecules would be made more complicated in their name. In this example, we can name the carbon between each ring as the main chain. The name of the molecule becomes di for 2, cyclohexyl cyclopentyl methane. We don't need to include numbers since there's only one place in a methane. What would happen if we tried to name it with IUPAC standard rules? Cyclohexane would be the main chain since it's the longest continuous chain, but the side chain would be a methyl side chain with 2 additional side chains. It would be a cyclohexyl cyclopropyl methyl cyclohexane. This is substantially harder to follow, so IUPAC lets us name it as a methane with side groups instead. In the last example, we had 2 cyclohexyl groups off the methane. We don't want to list these individually. That can be a huge pain in the large molecule. Instead, we'll just give the number of groups that are of the same type with a Latin prefix. Di for 2, tri for 3, tetra for 4, penta for 5, etc. These are the same prefixes that we use in general chemistry for naming binary molecular compounds. Every group comes with a locator number as well. These side chains are listed alphabetically by the name of the side chain, not the prefix, and definitely not the locator numbers. So if there's a di, the di isn't included as in the alphabetical order. In the example shown, the longest chain is the chain from left to right, or right to left. There are 6 carbons, so that chain has to be a hexane. The groups on the top of the molecule are both methyls, so we know it would be a dimethyl because there are 2 methyls. They are on position 2 and 4, so it is a 2,4 dimethyl. The other group is on the 3rd position and is an ethyl. Since E for ethyl comes before M for methyl, again ignoring the di, the whole molecule is a 3-ethyl 2,4 dimethyl hexane. When we have substitution on a ring, there's no clear starting or ending point until we substitute something onto the ring. If there is only one substituent, that position automatically becomes 1, and there's no need to number it. Pause and try to name the molecule shown. It's a methyl cyclohexane. Methyl because it has a 1-carbon chain coming off the side, and cyclohexane because it has a 6-membered ring. There's no number needed. As soon as we add more groups to the molecule, all the numbers are needed so you can tell which of the groups is being considered 1, and so that you can tell relative spacing. You can number around the ring in either direction, so choose the direction that gives lower numbers. If you have 2 groups on the ring that have the same priority, like alkyl chains, chains of carbons, just set the one that is lower alphabetically as the lower number. Pause and try to name these molecules. Bring the answers to class. The first is an ethyl 2-methyl cyclohexane. Ethyl for that longer chain, that would be the 1 position, and then 2-methyl for the chain that's 1 carbon away from it on the main chain. And the second name is 1,2,4 trimethyl cyclohexane. For the sake of talking about reactivities, we classify carbons based on how many other carbons are attached directly to that carbon. A carbon attached to 1 carbon is primary. A carbon attached to 2 carbons is secondary. 3 is tertiary, and 4 is quaternary. We generally don't write the words, but instead indicate with a number and a degree sign what type of carbon with which we are dealing. There is no reason the side chain needs to be straight. In complex molecules, side chains themselves often have side chains. So we could have an ethyl side chain with a methyl off the 1 position, so the whole side chain would be a 1-methyl ethyl with its own locator. This gets very complicated very quickly, so the most common branch side chains have special names that are often used and accepted in lieu of the more complex names. The list below has the most common names like this and needs to be memorized because no one is going to tell you that isopropyl alcohol is actually the same as the IUPAC named 2-propanol. In the list displayed, notice there are actually common names for the straight chains, the first column. These are used for clarity when common name forms are being used for molecules. The second column is all side chains where the last carbon of the chain is moved 1 position earlier. So the end of the chain is forked, which is the literal meaning of iso. Sec-butyl is just a butyl attached at the second carbon instead of the first, and tert-butyl is a butyl where a tertiary carbon is the point of attachment to the rest of the molecule. As a review, these are the rules for systematic nomenclature under the IUPAC system. In steps 1 through 3, we identify the main chain, the noun part, and steps 4 through 7, we further describe that main chain based on the side chains that come off of it. I want to give you a few chances to assess your own learning. In this problem, and all multiple choice problems, try to identify the correct answer before looking at the given answers. Pause to work on the problem. Do that now. The longest chain can either be right to left or left to right. Both 7 carbons and therefore heptane. So we know that we have a heptane to begin with. But left to right keeps more of the numbers lower. If we number from left to right, the numbers are 2, 3, and 6 versus 2, 5, and 6 if it's right to left. So we know we're going to number from left to right. Each of the side chains is a methyl, and there are 3, so the molecule must be a trimethylheptane. So a 2,3,6 trimethylheptane, and B would then be the correct answer. Try another one. Pause to work on it. The ring is only 3 carbons, but we can get 4 carbons in the main chain if it is just off from the ring all the way to the top right. Since 4 is larger than 3, butane will be the main chain with a cyclopropyl side chain at position 1. There is also a methyl at position 2, so 1 cyclopropyl, 2 methylbutane, which is E. Under systematic IUPAC rules, halides are always listed as substituents. To indicate this, the end of the halide is switched so that it ends in O instead of INE. So fluorine becomes fluoro, chlorine becomes chloro, bromine becomes bromo, and iodine becomes iodo. Nitro groups, NO2 groups, are also always listed as substituents, as well as ethers. Ethers are named in the form alkoxy. The oxy is just the oxygen that's attached to the main chain, and the alk is just the length of the carbon chain on the other side. Here are some examples of ethers for reference. Try to name these first, and then we'll go over them. The first molecule in the top left has the longest chain of 3 carbons. Notice the oxygen doesn't count towards that chain. So it's a propane. And off of the 1 position, we have a oxy that has 2 carbons on the other side, so an ethoxy. So this would be a 1-ethoxypropane. The next molecule would be a methoxy cyclohexane. Then we could also have a 2-methoxy 2-methylpropane. And finally, an ethoxyethane. People were naming molecules for a long time before nomenclature rules were made systematic, so IUPAC makes allowances for common name forms to be used. In common names for organic molecules that contain halogens, alkyl halides, we name the halogen as the main chain and everything attached to it as a side chain. So methyl iodide is used alternatively for iodomethane, or isopropyl chloride for 2-chloropropane. There are also a few molecules that have other names that don't follow this pattern, but are named with unique names like methylene chloride, chloroform, bromoform, and carbon tetrachloride, which is also commonly known as carbon tet. Ethers also have a form for common names. It is just the name of the carbon chains attached on either side as side chains in alphabetical order, followed by the word ether. It's actually a lot easier. So if the side chains are the same, we just use the prefix di instead of listing them twice. Pause to try to name the molecules shown with this pattern. So the first molecule we have would be an ethyl propyl ether, ethyl for the chain on the left, propyl for the chain on the right. The next one would be a cyclohexyl methyl ether, and a tert-butyl methyl ether, or methyl tert-butyl ether alphabetically, and then the last one would be a diethyl ether. Alkanes, alkyl halides, ethers, and nitros are some of the simplest molecules to name systematically since they don't have any functional group in the name. In the next chapter, we'll expand these rules to include functional groups that are more important, and we'll change the suffix of the molecule name.